All right, so we're going to go over 10.6, which is polar equations of conics. So we're going to go back to that polar idea. If you remember back to chapter 9, part 1, we learned about polars. If you think about polars was when we had our coordinate system that looked something like this. Our ordered pairs were r comma theta, right? So maybe it was 2 comma 90 degrees, which means towards the 90 degrees we went out 2 units, 2 circles towards the 90 degrees, okay? So that's our polars. So when we're talking about polar equations of conics, so we're going to graph conic sections on our polar plane and not just our xy plane. So when we talk about polars, one way that we can figure out what type of conics we have is by looking at our value that's called the eccentricity. Sorry, someone came to my door and I forgot where I was at. I believe I was talking about this E value, which means eccentricity. So the eccentricity of a conic is basically just a ratio that we make that talks about the distance from the focus to a point compared to the distance from the directrix to a point. So let's say I was talking about like a parabola. This was my parabola. Here's my focus, here's my directrix. Okay, and here's my point P. So let's say the distance from my point to my focus was 3. By definition, that means that the distance from the parabola to the directrix also has to be 3, because if I do 3 divided by 3, I get an answer of 1, and it says right here that the eccentricity is 1, then that means it's a parabola. Okay, so essentially we're saying when you divide our focus to the point divided by the point to the directrix, that tells you which conic section it is. So if it equals 1, it's a parabola. If that ratio is less than 1, so let's say something like 2/3, then that means it's an ellipse. And if E is greater than 1, then that means it's a hyperbola. This is something that I am asking you to remember. You do need to know this for the test, okay? You need to remember that E is equal to 1, then that means it's a parabola. If E is less than 1, then that means it's a conic, it's an ellipse. And if E is greater than 1, then that means it's a hyperbola, okay? You can always tell what our eccentricity is going to be by doing C divided by A. So for example, if I had an ellipse where our C value was 2 and our A value was 5, then that means our eccentricity would be 2/5. Okay, 2/5 is less than 1, so that's an ellipse. So I would know that as well. Now down here we're talking about our polar equations of conics. So our polar equations are going to look like one of these 4. So we have our eccentricity times P over 1 minus our eccentricity cosine of theta. We can have this exact same equation but an addition sign. We could have this exact same equation but with sine, and then also sine but with a subtraction symbol. Sorry, I got interrupted again. So anyways, these are going to be the 4 forms of our polar equations. Now, you are going to get to use this on your test. So I am not asking that you memorize this. Okay, you get to use this. But you're going to have to know how to use it. So I'm going to kind of keep this handy. If I were you, I would maybe rip it out of your packet. That might be helpful, so that you can kind of have it next to as we're doing each of these problems. So if we look at example 1 on the next page, it says identify the conic that each polar equation represents. Give the position of the directrix. Okay, so we want to identify and then give the position of the directrix. So in order to identify, I need to figure out what E is. And if we look at our sheet here, E is always the number that's in front of our sine or cosine as long as this number is 1. So if I look here, we have a 1 here, which means I'm going to match it up to one of these, and E is the number in front of the sine or cosine. Well, the number in front of sine or cosine in this example is 1. So that means E is 1. And I told you to remember that if E was equal to 1, then that means it's a parabola. So this means that our conic is a parabola. Okay, now, it also wanted us to give the position of the directrix. So in order to give the position of the directrix, we're going to use this little chart. So we've got a 1 plus sign. So if I look here, 1 plus sign says the directrix is parallel to the polar axis at distance p units above the pole. So we're basically going to copy that down, but we have to figure out what p is. So I'm going to copy that down. The directrix is parallel to the polar axis, sorry. P units, which we got to figure out, and it said above the pole. Okay, so it's going to be parallel to the polar axis, P units above the pole. So to figure out P, if we look at our equation here, we got E was 1 by looking right here. And if we look at the top, E times P gives us the top number. So I know that E times P had to give me 17. And if I know E is 1, well, that means P has to be 17. So it's going to be 17 units above the pole. So what is that saying? If we had our polar axis, right, and we had our circles here, it's saying the directrix is parallel to this line. This is our polar axis, so it's going to be parallel 17 units up. So our directrix is going to be right here at 17. Or in rectangular form, y equals 17. Okay, so let's look at example B. So in example B, we've got 11 over 4 minus 5 cosine. Now remember I told you that the number in front of sine or cosine is going to tell us E only if this was 1, and it's not, it's a 4. So I cannot use 5. So what we're going to do is we're going to say, well, I need this to be a 1, not a 4. So if I divided it by 4, wouldn't that give me 1? But if I divide that by 4, then I also have to divide everything else by 4. So that gives me the equation 11 over 4 over 1 minus 5 over 4 cosine theta. So now that it's in the right form, I can say, oh, well, that means that E is 5 over 4. Don't worry about the negative. And if it's 5 over 4, that means it's greater than 1, which means it's a hyperbola. So this means it's a hyperbola. Okay, now let's figure out the directrix. So this is 1 minus cosine. So if I look on here, 1 minus cosine says the directrix is perpendicular, distance p units to the left. So I'm going to copy that down. So the directrix is perpendicular, so that's the key word there, is perpendicular, parallel versus perpendicular, to the polar axis. P units, and then this one said left of the pole. Okay, so these are the words that are going to change each time. Perpendicular or parallel, the units change each time, and it's going to be left, right, above or below. So that word's going to change depending on which one we pick. So just like in this problem, E times P has to give me 11 over 4, because that's this number here. And we said that E was 5 over 4, so 5 over 4 times P equals 11 over 4. Using our algebra, I can multiply by 4 on each side. Oh, that cancels that out. 5P equals 11. divide by 5 on each side, we get P is 11 over 5. So 11 over 5 units to the left of the pole, which means for a visual, it's perpendicular to the pole, to the polar axis. So if this is the polar axis, it's going to be perpendicular to the left 11 over 5 units. So there is our directrix, perpendicular to the pole. All right, so given all that, we're going to have to do that same information when we want to graph our conics. So in this first example here, I want to graph it, but I need to do all of that same information. So the first thing I have to do is remember this has to be a 1, and in this problem it is not a 1. So our first step here is we have to divide each of these by 2 so that this can turn into a 1. So we end up with 4 divided by 2 would be 2 over 1 minus, now this is like 1 over 2, so it would be a half sine theta. So because this is a 1/2, that means E is 1/2. If it's 1/2, that's less than 1, which means this is going to be an ellipse. Let's figure out what P is. So E times P is going to give me 2. I know E is 1/2. Multiply by 2 on each side, we get P is 4. So it's an ellipse where P is 4. This is a 1 minus sine, so 1 minus sine, a directrix is parallel, P units below. So the directrix is parallel 4 units below. Okay, I just copied it down from the sheet, and remember, you get to use this chart on your test. So you do not have to memorize this, you're just copying it down. So that means that our directrix is 4 units below, and it's parallel. So 1, 2, 3, 4. Here is our directrix. It's parallel to this one, and it's 4 units below the pole. Now, to get our graph, we're going to have to make an XY chart. Except because we're in polar, it's going to be an R theta chart. Now for theta, we're going to choose 0, 90 degrees, 180 degrees, and 270 degrees. I sure hope you haven't forgotten about your unit circle, because we're going to be talking about unit circle right now. So I need to plug 0 degrees into this formula. So I've got 2 over 1 minus a half sine of 0 degrees. Well, sine of 0 degrees, I hope you haven't forgotten about your unit circle. Sine of 0 is 0, so 1/2 times 0 is 0, so we end up with 2 over 1, which is just 2. Okay, now let's plug in 90 degrees. 2 over 1 minus a half sine 90 degrees. Well, sine of 90 is 1, so 2 over 1 minus a half would be a half. 2 over a half is 4. 180 degrees. So if I make this a 180, it's going to be 0 again, which means we're going to end up back at 2. Okay, 2 over 1 minus sine 270. Sine, oops, I forgot about the half. 270 of sine is negative 1. So we end up with 2 over 1 plus a half, which gives us 2 over 3 over 2, which ends up with 4 over 3. So now let's graph these ordered pairs. So towards 0 degrees, we're going to go out 2 units. Towards 90 degrees, we're going to go out 4 units. Towards 180 degrees, we're going to go out 2 units. And towards 270 degrees, we're going to go out 4 over 3, which is 1 1/3. So here is our ellipse. This is what an ellipse looks like in polar form, not in rectangular form, but in polar form. This is what an ellipse looks like. Okay, so let's look at example B. I would suggest you try to do example B on your own. Pause, try it. If you get stuck, on pause, and we'll do it together. So if we look at example B here, first thing we have to do is make this a 1, so we're going to divide each of these by 4. So we end up with 9 over 4 over 1 minus 7 over 4 cosine theta. Because this is a 7 over 4 for E, that means it's going to be a hyperbola. So when we graph this, it should look something like a hyperbola. We need to figure out P. So 7 over 4 times P equals 9 over 4. When we solve for P there, multiply by 4, divide by 7. We end up with 9 over 7. So P is 9 over 7. Let's look here. It's 1 minus cosine, 1 minus cosine. Copy this down. Directrix is perpendicular, P units left. So directrix is perpendicular, P units, so 9 over 7 units to the left. So 9 over 7 units is a little over 1. So if that was 2, let's say our directrix is right here. So there's our directrix. Now to get the other points on our plane, we're going to have to create our R theta chart. We're going to do 0, 90, 180, 270. We're going to plug in our values into our equation. So if I plug in 0 in for cosine, I get 9 over 4 over 1 minus 7 over 4 times cosine of 0. Cosine of 0 is 1. 7 over 4 times 1 is 7 over 4. So 1 minus 7 over 4, 9 over 4. Why don't we just use our calculator? So we get 9 over 4 divided by, I guess I should have made a fraction here. 9 over 4 divided by 1 minus 7 over 4 gives us negative 3. Cosine of 90 degrees is 0, so that's going to drop out, leaving us with just 9 over 4 divided by 1. 180 degrees is going to make cosine negative 1, so that's going to turn this to a plus. Once again, if we don't know our unit circle anymore, we're in trouble. Go learn it. Okay, that gives us 9 over 11. Then 270, that's going to be 0 again, cancels out, just 9 over 4. So at 0 degrees, I'm going negative 3. So at 0 degrees, I'm going to go 1, 2, 3. Right? Remember, when we're talking about polars, negative means we're going in the opposite direction. So I'm not going to go 3 units towards 0, I'm going to go 3 units away from 0. At 90 degrees, we're at 9 over 4, which is a little over 2. At 180 degrees, 9 over 11, which is a little under 1. And then at 270, we're back to 9 over 4, which is a little over 2. So what happens is we have our hyperbola here, and we also have our hyperbola over here that matches. So there is our hyperbola in the polar plane.